We're now going to talk about some general experimental considerations that we have with extraction. The first of these is a safety issue. It turns out that when we do an extraction, there can be a large pressure increase in the extraction apparatus. The concern about this is that during the extraction, when we're shaking the mixture of two solvents in order to have them break up and have a large surface area between them, the apparatus will probably be sealed. Creating a pressure increase inside a sealed apparatus can be very hazardous because if the apparatus cannot hold the increased pressure, it can cause it to essentially shatter and spray solvent and glass all around. This is pretty dangerous. Now, why would there be a pressure increase? Well, this occurs because of vapor pressure. Every solvent is going to have a vapor pressure when it is in contact with a gas phase. The vapor pressure basically just represents the fact that molecules within the liquid will be moving in all directions, and often they will be moving essentially at an angle sort of perpendicular to the interface. Not a perfect 90-degree angle, but at an angle that move them toward the direction of the interface. When they hit that interface, some of those molecules will have enough kinetic energy to break the attractive forces that they have with other solvent molecules and launch up into the gas phase. This then represents the pressure that would be given off when this solvent is allowed to stand in a closed container with a vacuum above it. What's the maximum pressure that would be reached? That's the vapor pressure. Now, if we look at a container like this, where we have two liquids, liquid A and liquid B, liquid A forming a layer on top, liquid B forming a layer on the bottom, and the container is open, what we would see is that the pressure inside the container would basically be the same as atmospheric pressure. So we will call that P sub A. I'm sorry, P of the atmosphere. There will also be a vapor pressure of molecules A inside the container. We will call that the partial pressure P sub A. Now, there will not be a significant amount of B molecules in this gas phase because B is covered up by solvent A. So therefore, we will have the pressure inside be P atmosphere, and that will be the partial pressure of substance A plus the pressure of air that remains to bring it up to a total of atmospheric pressure. If we just let this stand, this very rapidly reaches an equilibrium, and the pressure inside and outside would be identical. If we now seal up the container and shake it, what will happen is that layer B will begin to come into contact with this gas phase. Now, I've represented this just by imagining the two layers turned sideways, where they contact the gas phase on the end of their layer. But really what we have is these layers break up into a large number of small globules that sort of intersperse among each other. However, the point is that when layer B is now able to come in contact with the gas phase, it will begin to release molecules up to its vapor pressure. So we see now that in our sealed system, our total pressure will be the pressure of air from before we sealed it, plus the vapor pressure of A, plus the added vapor pressure of pressure B. So the internal pressure now, when it's sealed, will be P of A plus P of air plus P of B. But if we look above, P of A plus P of air is just our initial pressure. So now what we have is an additional vapor pressure of B amount of pressure inside. The pressure will be higher. P internal is now higher than our initial pressure. Again, depending on how high this vapor pressure is, this could be very hazardous. So what do? Well, as a safety measure then, when we seal the container and begin to shake it, what we will do is shake for a small period of time, then reopen the container to allow the internal pressure to equilibrate with air pressure, seal it again and shake, and continue that process of shaking and venting until there is no more pressure being built up. We have sort of equilibrium of the two vapor pressures inside. Then it will be safe to shake for an extended period of time. The next consideration that we have is what's called an emulsion. When we shake these two immiscible liquids, they will break up. These layers will break up into smaller, what we would call globules, little circular or roughly spherical packets of the liquids. And those globules will be sort of mixed and stacked with each other. This is actually technically called an emulsion. Normally, we expect when we stop shaking and let the mixture stand, that those globules will begin to strike each other and combine, eventually reforming the two layers. However, sometimes we find that the layers will not completely reform. We'll get a layer on top, a layer on bottom, and then in between them, we will get a remainder of the emulsion, which will look sort of like a foam in between the two layers. We generally call this then formation of an emulsion, meaning that it forms and won't separate. Emulsions are really a nuisance. They can take a long time to separate. We especially see emulsions when we use organic solvents that are very nonpolar, so that they don't really have a lot of attractive force. Some examples of these are things like hexane and dichloromethane in particular. Dichloromethane is notorious for forming emulsions that won't separate. How do we deal with this? Well, when an emulsion is likely to form, we try not to shake very vigorously. We don't want to break those layers up into globules that are too small. So if we shake really strongly, we'll break it up into very small particles and they won't separate from each other. It's also possible, if we're working on microscale, in which we use centrifuge tubes to conduct our extraction, that we can centrifuge the emulsion. Centrifuging forces the denser layer down to the bottom and sort of squeezes the less dense layer up to the top. So that can help separate the two layers. There's other methods. Often stirring with a stir rod will help. And there is, even for certain solvents, special filter paper that can be used that will filter out one solvent while leaving the other solvent trapped behind.